This is an excellent paper. It's one in a series of excellent papers we've gotten to enjoy at this conference. So I want to add my thanks to Abner and Jim for organizing such a great conference. I actually saw this paper last spring at the Texas Finance Festival, and I told Constantine I'm indebted to him because the work that he mentioned that I've been doing on this topic in the Kyle framework was inspired by thinking about his paper last spring. To recap the main points, we have a friction in the credit market, which is illiquidity in the secondary bond market. And that impacts, of course, the bond values because bond investors realize lower cash flows due to this illiquidity. And that affects the firm's default decision. So Constantine separated models that look at liquidity as a function of default, and default as a function of liquidity. And this paper is looking at both. It marries the DGP model and Leland-Toft. And I should say that it's a little bit surprising that this wedding goes off as smoothly as it does. They have to solve the differential equation from the DGP model to get bond valuation, and then plug that into the Leland-Toft ODEs to solve for equity valuation. And it's quite surprising to me that they were able to get a closed form solution for this. So technically it's quite impressive. Okay, an antecedent, as Constantine mentioned, is the paper by Ziwo and Wei Zhang and JF last year, which also does a Leland-Toft model and also has illiquidity in the secondary bond market. But in that paper, the illiquidity is exogenously given. So we have a fixed cost of transacting in the secondary market. And that impacts the default decision. So Ziwo and Wei look at the relationship between the illiquidity in the secondary market and the default decision. And what this paper is doing is looking at the other direction as well, how the default decision, how credit risk impacts the liquidity of the bond. And to do that, of course, they have to bring in a model of the market microstructure, and that's the Duffy-Garliano-Peterson model. And because they endogenize this discount in the secondary market, they're able to look at how the discount varies with market situation. And so they show that it's lower for short maturity debt, which is very sensible. And also, and this is the crux of the paper, the cost in the secondary market is higher for lower rated debt when you're more near the default boundary. Actually, that's true under some conditions. As Constantine mentioned, there's some subset of the parameter space for which that's true. A small point is that it would be useful to know more about that subset. Is that quite generic? Is it going to be quite common that we have this connection between credit quality and liquidity? It's certainly true in their calibration, but it'd be interesting to know more about the nature of that subspace of the parameter set. Okay, so I want to go over the microstructure model a little bit. I'll have a couple of comments about that, and I'll have a question about the capital structure model, and those will be my comments. This notation actually is from Duffy, Garliano, and Peterson. There are three types of investors. They're high and low. Low is after you have the liquidity shock. You have a lower value for the bond. You have a holding cost for holding the bond. In this model, the low types exit after selling. So we only have three types that are active in the market. The ones who want to trade, the high types who don't own the bond, and the low types who do own it, have to wait to trade because they're matched. They have to wait a random time before being matched with dealers. So these random matching models, of course, have been around for a long time. And what Duffy, Garliano, and Peterson do is they marry the matching model with intermediation. So we have a random matching model with dealers involved. The dealers don't hold any inventory. They simply sell in the interdealer market instantaneously to transfer from the seller to the buyer. And every time a dealer and an investor are matched, they do Nash bargaining. Now, Constantine said that it was beyond the scope of the paper to endogenize the relative masses of these different investor types, which determines, of course, the values of the investor types. So one way to think about it is that you have an infinite mass. You have just a very large number of potential buyers of the bond pre-default. Okay, so even though you start with an infinite mass, some of these guys exit, but you always have an infinite mass, so you're in steady state. Now, because we have so many of these guys, they don't earn any rents. They're rationed in equilibrium, and so they're not going to earn any rents. And because we have so many potential buyers who are matched with dealers, the dealers who are matched with buyers also don't earn any rents. So the rents are going to go to the seller of the bond and the dealer with whom he's matched. They'll split the surplus, the gain from trade. So when you think about the firm issuing the bond, the buyer of the bond, the high type, anticipates that at some random time he could become a low type, and then he's going to have the holding cost of bearing the bond as the low type until he's matched with a dealer and can trade. And then when he does get matched and can trade, he's going to lose some surplus. So we have costs coming from both of those aspects. Now, quite naturally, the costs are less for short-term debt because the secondary market's just not as important. You can sell the bond back to the firm at maturity and not have to deal with giving surplus to a dealer. Okay, so I have a couple of comments about really parameter values that I would choose for the calibration. And this is really about Duffy, Garliano, and Peterson more than it is about this particular paper. They just borrow this structure, as I said, from Duffy, Garliano, and Peterson. I don't really understand random matching with dealers, to be honest. If you sell your car privately, you stick a sign on it and drive it around, or leave it parked in your driveway, or you're selling a house, you have to wait a random time to find a potential buyer. Right? But if you want to find a bond dealer, you just call him. Now in the calibration, it takes on average 3.5 weeks for an investor to find a dealer. Right? So one rationale for this might be, well, it takes a long time for an investor to execute a very large bond trade because they want to split it up into pieces and sell it a little bit at a time. But there's a big difference between being forced to wait weeks and choosing to wait weeks. And if you're in the model, you're an investor, you meet a dealer, the dealer knows that if you don't agree with him, if you walk away, you're forced to wait on average 3.5 weeks before you can find somebody else to trade with. If you're just trading with him a small piece and then you're going to trade with somebody else a small piece, he doesn't have the same leverage over you in the bargaining game. Right? You're giving bargaining power to the dealers because it takes you 3.5 weeks to find the phone number for Goldman's bond desk, right? So that just seems unrealistic to me. But it's easy to remedy that. Just make the waiting time go to 0, which means make this intensity, this matching intensity, go to infinity. Now, that takes rents away from the dealers, but I'd be happy to give rents back to the dealers by making another change. So, Nash bargaining. Again, this is from the DGP model. Now, of course, Nash derived the bargaining solution axiomatically. But the real justification for it is Rubinstein's alternating offer game, right? That's the non-cooperative foundation for the Nash bargaining solution. Well, I don't know for sure, but my impression has always been that when an investor calls a dealer, the dealer quotes both sides. And there's typically not a lot of negotiation that goes on other than the investor saying yes or no to those quotes. Right, so it seems more reasonable to me to assume that dealers make take it or leave it offers. That's the assumption, for example, in Hao Zhangzhu's paper that was presented here 2 years ago, by the way, and appeared in RFS last year. So let's suppose dealers make take it or leave it offers. Now you have potentially lots of equilibria, in particular the equilibria that they look at where you have this division of the surplus, potentially. It depends on whether there's a cost to saying no to one dealer and then going to another one, whether the delay between turning down one dealer and calling another, whether that delay is costly. Okay, so suppose the delay is not costly. Then there's an equilibrium in which the surplus between the dealer and the investor is split in any arbitrary way. Right, so the equilibrium is all dealers quote the same thing. No dealer would ask for less. And if any dealer asks for more, the investor walks away, goes to another dealer. It's okay? So that supports the equilibrium with an arbitrary division of the surplus. But if it's costly, even epsilon, to turn down one dealer and go to the second, then the first dealer you call we have this division of the surplus we're trying to support as an equilibrium. The first dealer will undercut by epsilon over 2. He'll ask for epsilon over 2 more of the surplus. And of course, because it costs epsilon to go to the second, then you're going to, that undercutting will destroy the equilibrium, right? So the only equilibrium that survives this undercutting is where the dealer gets all of the surplus. Okay, so that's the diamond paradox, that in the search model, dealers, stores, retail locations, whoever is setting prices, can capture all of the surplus. And to think about why it's a paradox, it's useful, I think, to think about the Kyle model in comparison. So the Kyle model assumes that investors can get the dealers to participate in an auction. So the dealers compete against each other in a Bertrand fashion. And that means that the investor captures all the rents, all the gains from trade. Now, if instead of having the dealers bid simultaneously, they bid a second apart, and there's epsilon cost to waiting that second, then we go from the investor getting all the surplus to the dealer getting all the surplus, right? The dealer getting all the surplus seems like a reasonable solution to me, even though I spent most of my career working on Kyle models. Right? I like the dealer getting the surplus here. Okay, so I have a question about the post-default model about steady states, but it's minor, so I'll let that go for now. So I have one question about capital structure. So Leland-Toff model, you have fixed maturity debt. And when debt matures, you issue new debt of the maximum maturity. And so you have this constant maturity structure over time, and that makes the analytics possible. Now that's probably fine for Leland and Toff's purpose, but I'm not sure it's a reasonable assumption here, right? The problem is the commitment. And so this paper shows that when you get near default, the illiquidity problem in the secondary market becomes larger. But it also shows that the illiquidity problem can be ameliorated by issuing shorter term debt. So it seems very plausible that it's going to be ex post optimal to shorten your maturity structure as you approach distress, right? And of course, if investors will anticipate that you're going to do this ex ante, and so that's going to affect all of your bond issue prices. So I don't know if it's possible to solve with ex post optimal maturity, but at least there should be some discussion, I think, in the paper of this issue, right? Because the liquidity spiral is really the heart of the paper. That's the relationship between approaching distress and the illiquidity in the secondary market. And I think that's going to drive corporate decisions in a particular direction, which may undo some of the damage that liquidity spiral causes. Okay. So, summary. It is very impressive on the technical dimension to be able to marry these two models together. I was surprised that you could get closed form solutions when you put these two things together. And it's very nice that they do get this endogenous liquidity, varying both by maturity and by credit quality. So that's a very nice contribution. And I have a few minor suggestions that I went through.